on optimal control and stabilization of vectors.
Right, thank you so much. First of all, I would like to thank the organizers for inviting me here and for giving me the opportunity to share some of the experience we have had solving different kind of control and optimization problems for fluid systems. And at this point, let me also maybe add that it's my first time to India. I've been here for more or less 30 hours, and so far I have had terrific experience. Okay, so I guess I'm here to tell you something about the various methods that we can employ to solve real problems involving control and optimization in fluid mechanics. So what I would like to do is I'll try to offer you a glimpse of different tools that can be used for that purpose, and the emphasis here will be mostly on computation. So while I will refer to a handful of results from analysis, I guess most of the focus in this presentation will actually be on computation, on the use of various analysis-motivated methods for computational solution of actual problems. So, as Paul said, I'll be giving two talks. In the first talk now, I'll focus on some classical problems. So problems that people in the community worked on maybe in the 90s, and which were solved. And I had, I guess I can say that I had the pleasure and the privilege to participate in that effort. So those problems are sort of classical now, and I'll offer a brief introduction to a computational solution of those problems. And I guess my second presentation tomorrow would be devoted to some emerging problems, including some non-traditional applications of control and optimization to problems in theoretical fluid mechanics. Okay, so so here's the outline of my the first part of my presentation. I'll start with some motivation, and then I will discuss two classes of problems. The first problem is the problem of determining optimal open loop control, which will frame as a solution of a suitably defined PDE constraint optimization problem. And I'll show you how this problem can be set up and solved computationally. And the key ingredient of the approach will be calculation of an object we call the gradient. Okay? And I'll show you how this can be done elegantly and efficiently using the so-called adjoint equations. Okay? And the second part of my presentation today will focus on some rather simple feedback control problems, again involving fluid mechanics, where a solution will be obtained using using tools of linear control theory, pretty much in the spirit of the approaches that Professor Raymond described earlier today. So this will be a rather simple problem. However, because of the simplicity, we'll be also able to make some forays into the nonlinear regime and say something about the full nonlinear problems. Okay? And then, time permitting, I'll try to say something about a class of inverse problems, which we call the vortex design problem, which will be formulated in terms of some free-boundary problems for Euler equations. Okay? And again, let me reiterate one more time that in my presentation, the focus will be on the design and in implementation and a bit of analysis of efficient computational tools in view of their ultimate application to real-life problems. So in terms of motivation, a recurrent theme of my lectures will be the control of vortex flows. So there are two sort of model. There are two situations where there are many situations where control of vortices becomes relevant. Let me mention just two. One is called the so-called wake hazard. It's a well-known fact from aerodynamics that when a plane takes off, in order to be able to generate lift, it must leave two huge trailing vortices behind itself. And when you're in a plane at the major airport sitting on the tarmac and waiting for your time to take off, the time that has to elapse between the takeoff of two consecutive planes is actually what is required for those large vortices to dissipate. So if something could be done to somehow reduce the intensity of those vortices, this would be actually quite beneficial. Okay, and there have been a number of disasters where planes actually took off too early and got in the wake of the previous plane, and really bad things happened. Okay, and the second motivation comes from the area of fluid structure interaction. So that's it's a still figure from the so-called Tacoma Narrows bridge disaster. There was a bridge just south of Seattle in Washington State in the U.S., which collapsed. And what happened was that when the wind was blowing along the river canyon, the natural frequency oscillations of the bridge happened to coincide with the frequency with which the vortices were being shed. So the disaster, the collapse of the bridge, was the consequence of the resonance. So again, vortices played a major role there. So in fluid mechanics, we've tackled a number of different problems. They are all governed by various versions of the Navier-Stokes equation, which can be formulated on different domains with suitable initial and boundary conditions. I guess a number of things have probably been already said during this winter school as regards this equation. And we studied different configurations, some simplified PDE models, flows past bluff bodies, flows in the channels. In this presentation, I'm going to squarely focus on this configuration that we call the bluff body wake. Okay? It's one of standard problems studied in fluid mechanics. Let me show you a video that illustrates what is happening. So imagine you have an obstacle. First of all, let's consider the domain, which is infinite. Okay, so it's just R2 minus this obstacle, which is just a disk. We have a flow oncoming coming from the left with some uniform velocity profile. And if the Reynolds number is sufficiently high, what happens is that we observe spontaneous appearance of counter-rotating vortices, the so-called Bernard von Karman instability. What happens is that as soon as those vortices appear, then the drag, which is the force that is acting on the obstacle, significantly increases, as do the fluctuations of the lift, so the force in the transverse location, both of which are rather detrimental effects and are source of a lot of problems. So controlling this flow has been the holy grail of the fluid mechanics community for many years. And this flow itself, because of the richness of features resulting from a very simple setup, has come to be regarded as the hydrogen atom of fluid mechanics. Okay, so this is the flow that everybody is studying because of the richness of different phenomena that are evident in this admittedly very simple setup. Oh, sorry?
Vortex.
Yes. Okay. So yes, that's a good question. So what we see here are the time-dependent fields of vorticity. If we have a velocity field, okay, so the velocity field V for every time t is a function defined on the domain omega in our two-dimensional problem, whose values in R2. So vorticity is a scalar which is defined as partial V y partial x minus partial the x partial y. Okay, this is what we call vorticity. Okay, and vorticity is a key quantity of interest to fluid analysis. Okay, so what we see here are is the time evolving field of vorticity, where the blue color corresponds to the negative vorticity. So fluid is spinning clockwise, whereas the red corresponds to negative vorticity with fluid spinning counterclockwise. Okay. So I would like you to bear in mind this picture as we move on discussing various problems. So let me emphasize that the goal is to control this flow, and I'm going to present two different approaches to do this. And again, let me emphasize that this is sort of classical work that was developed in late 90s, maybe early 2000s. Okay. And by all means, should you have any questions in the meantime, please do not hesitate and just ask them. Okay, I'll be very happy to.
What is the third picture?
Oh, the third picture, that's a third type of flow that has been an object of investigation, which represents turbulent flow in the boundary layer. Okay, so you have a wall, which is green, and you have a turbulent boundary layer, which is characterized by the spontaneous appearance of so-called streaks, which are some complicated vortices forming the boundary layer, which are visualized here in blue. Okay. All right. So yes, part one, open loop control via adjoint-based optimization. So here is the setup of the problem. Domain is infinite. We have an obstacle, and well, if we want to set up a control problem, first we have to think about what sort of actuation we are going to use, namely how the control authority will be exercised on the flow. And there are many different ways in which this can be done for this problem. Some are more realistic, some are less realistic. One type of control that has been considered in the fluid dynamics literature is simply by rotating the obstacle. Okay. So what we are going to do is we'll try to rotate the cylinder, and in doing so, we'll try to somehow control the flow. So mathematically speaking, what we are going to do is the control action will be represented by the boundary conditions in the Navier-Stokes system describing this problem. Okay. Some assumptions. Again, the flow is viscous and incompressible, two-dimensional, domain is infinite. Reynolds number in the application that I'm going to show is equal to 150. Okay. Okay. So in this, well, if you want to come up with an optimal formulation, then optimality must always be defined with respect to certain criteria. Okay. In other words, we have to come up with the cost functional that will represent the objective that we'll seek to achieve. Okay. So in our problem, the cost functional will represent the sum of two terms. The first term will be the power related to the drag force. Okay. So I told you that once those vortices appear, the drag force jumps up, and what we are going to do, what we are going to try to do, is to reduce the drag force. Okay, and it will be measured by the first term. Okay, and then at the same time, we would like to do so by expending the least amount of energy possible. Okay, so we want to exercise order epsilon effect on the flow in order to achieve order 1 result. That's the goal. Okay, that's why it is important to measure both. Okay. So, well, using well-known results from fluid mechanics, we can express this cost functional in the following way, where this term represents the force, this gives us the torque, and this gives us the drag. Okay, this is pressure. This is the normal vector. This is viscosity. D of v is the symmetric part of the velocity gradient tensor. When we compute drag, then force, then that's how this is done. Maybe I'll write some explanation here. So this is a winter school, then I'll try to be more explicit than what is just written on the slides. So if we have an obstacle, okay, then the force acting on the obstacle can be computed in the following way. This is an integral over the boundary, which we denote gamma 0, okay, of minus pressure times the normal vector plus u d of v, the sigma, where d of v is the symmetric part of the velocity of the velocity gradient tensor. Okay. Okay, and we want to minimize this cost functional subject to a constraint which represents well, all the equations that govern the process, which in our case happen to be the incompressible Navier-Stokes equation. So we have the momentum equation, we have the continuity equation, okay. We have some initial condition, which happens to be 0 at the initial instant of time, and some boundary conditions. Okay? And this is where things become interesting, because we see that our control variable, which seems to be the rate of rotation of the obstacle, okay. So the control problem is to find the optimal rotation rate, okay, as a function of time, that among all functions in a certain class will give us the smallest possible value of the cost function. Okay? So phi star represents the rotation rate, and it is related to our governing system by the boundary condition. Okay? So the control variable enters the constraint equation through the boundary conditions, and this is the quantity that we'll seek to determine, for which we'll seek to find the optimal solution. So I guess at this point it is clear that what we have is actually an instance of the so-called constraint optimization problem, which in an abstract sense can be written as follows. We are seeking the minimum of the cost function with respect to the state and the control when the state and the control are constrained by some equation. Okay. Now, from the computational point of view, this formulation, although very general, is not very convenient for the following reason. If we are trying to minimize the cost function simultaneously with respect to the state and the control, then this will typically result in discretized spaces over which we have to find a solution, which will have an enormous dimension. Okay? So for problems like of this type, it is often quite convenient to convert this formulation to the equivalent unconstrained formulation, where subject to some assumptions on how the state depends on the control, we can construct a so-called reduced cost functional, which will only depend on the control variable, okay? Which will not explicitly depend on the state variable. Okay? And then we consider the first order optimality conditions, which require the vanishing of the Gatot differential, okay, defined in this way. So I think what I would like to do now is I would like to work out with you a very simple example, which has exactly the same mathematical structure as the problem I have just formulated, yet is given in terms of a much simpler constraint equation, namely the heat equation. Okay? So in doing so, we'll be able to retrace all elements of the algorithm which are really important for computation. Okay? So The idea is that we'll have a simple example where we can work out all the details explicitly. The problems that I'm describing here have essentially the same mathematical structure. However, the details are much more complicated, and as such, they are probably too onerous to be covered during a lecture like this. But a simple heat equation is probably fine. Okay. So what I will like to do now is maybe switch to the Blackboard, and I will show you how to construct a solution algorithm for a very simple problem involving heat equation. Okay? So maybe I could ask how to just raise the. Yeah, I guess I can do this here. All right. Maybe you can turn off the data projector. All right, so let's consider space-time domain. Let this be Rn. This will be our domain omega. This is the time axis, okay? And we'll consider a heat equation. Defined on this space-time domain where the terminal time is t in 0t cos omega. Let's say that we'll have some boundary conditions given by B and some initial condition u0. Okay, this is going to be the equation, the constraint equation. Maybe just to fix attention, let's consider the one-dimensional case, in which case we'll have two boundary conditions. U at 0 is equal to, let's say, V A, and U at 1 is equal to V B. Okay? So that's our governing equation. And let's think of the following situation. Imagine that this equation describes, say, heat transfer in a rod. Okay, so a typical problem arising in applications is the following: how to manipulate the temperature at one endpoint so that the flux at the opposite endpoint will achieve some prescribed values. In particular, will follow some prescribed history in time. Okay. So let's imagine that at the left boundary, okay, we will have we'll define the quantity W, which will be the heat flux, which will be some prescribed functions of time. Okay, and what I would like to do is manipulate my Dirichlet data on the right endpoint, so that at the left endpoint we have precisely this heat flux. Okay. So phi will be my control. Well, how do we set up this problem? Well, our control will be a function of time, and to fix the tension, we can assume that phi will be an L2 function on that interval. Okay. Let's see. Okay, so we'll set up a cost functional, which will be defined on basically L2 t with values in R. So what form could we give to our cost functional? Well, it will depend on phi, and one possibility that is very often used in applications is to define this cost functional as the least square measure of the misfit between the prescribed profile of the flux at the left boundary and the actual profile. Okay? So the prescribed profile, okay, so we need an integral, 1/2 in front of it, integral from 0 to t. The prescribed profile is given by our function w, and the actual profile is simply given by partial u partial x, evaluated at the point 0, dt squared. Okay, and this solution u depends on our control phi. Okay, so we are trying to. So our optimal control, I'll define as phi hat, will be the arg min of j of phi for phi in L2 of 0t. Okay? Now, of course, it is by no means clear that at the optimum the cost functional should be 0. So it requires much more analysis to show that we can match exactly this. So in this formulation, we are just looking for the least square formulation, regardless of whether it can exactly reproduce the prescribed profile. So using the L2 norm corresponding to the least squares formulation is quite natural, because this gives us to a nice structure in the Hilbert space. In principle, one could also use other norms, for instance, some LP norms or even L-infinite norms. However, things become more complicated from the point of view of design of the computational algorithm, because such cost functionals are not necessarily differential. So things become more and more complicated, although it's still feasible. That said, such techniques are certainly far from being standard. Okay, so we are trying to minimize this cost functional with respect to the control phi, which enters through the boundary conditions of the equation which constrains the evolution of u. So that's how things are related in the problem. Okay? Okay, so how can we go about solving this problem computationally? Well, computationally, we will set up an iteration, okay, where we will start with some initial guess, phi1, which will be given by some rather arbitrary initial guess, whatever, 0. Okay? And then we will repeatedly update the approximation of the optimal control using the following algorithm. Okay, and I'm going to explain what is what in this formula in a moment. So you can think about this approach as a discretized version of a gradient flow. Okay, so imagine that we are in the control space, which in our case is L2. Okay, and we have a gradient of the cost functional that we can somehow compute. I'm going to show you in a moment how this can be done. And then what we do is we are flowing in the negative gradient direction until we hit a critical point, so that we can go. There's one more element which I probably should have stated earlier. So how are the optimizing solutions characterized? Well, they are characterized by the first order optimality conditions. Maybe I'll write them here. First order optimality conditions. Well, what we need is the vanishing of the Gateau differential. So if we define the Gateau differential in the following way. So j prime of phi in the direction phi prime. It's equal to epsilon minus 1, j of phi plus epsilon phi prime minus j of phi. Okay? This is what we call the Gateau differential, which is nothing else but the generalization of the directional derivative for the case of differentiation, general differentiation in function spaces. So this expression actually depends on two objects, phi and phi prime. Phi is where we compute the derivative, and phi prime in what direction. Okay? So in this definition, we can now state the first order optimality conditions in the following way. For all phi prime in our space, which is L2, okay, the Gateau differential computed at phi hat in the direction of phi prime should vanish, where phi hat is our minimizer. Okay. Now, so.
You want to leave it as a discrete quotient, or you want to take epsilon as discrete?
Oh yes, of course. I'm sorry. Of course. Yes. Make it straight, of course. Probably my jet lag. Yes, of course. We need to take this step. Okay. So these are first order optimality conditions, which, to be precise, characterize only critical points, not only maximizers or minimizers. It will also vanish at saddle points. In principle, for completeness, we would also need second order optimality conditions. However, exploiting them in computations is much more complicated, and I'll not discuss this. It's certainly possible, just somewhat more complicated. Okay, so if we discretize the gradient flow using this iterative descent algorithm, then it will converge to points which satisfy this first order optimality condition. Okay, so then the phi hat is the limiting solution of this sequence obtained by when n goes to infinity. Okay. Phi m. Okay, so when we take those iterations and we take sufficiently many iterations, then we'll get sufficiently close to points satisfying this condition. Okay, so these guys are just the consecutive approximations of our control. Tau n is the length of the step that we take along the gradient direction, and in a moment I'll discuss some techniques for determining this number. However, by all means, the most important element of this algorithm is this object, which we call the gradient of the cost functional. Okay, what does it represent? Well, it represents the sensitivity, the infinite dimensional sensitivity of this cost functional, of this object, to my control, which is the boundary condition. Okay, so it's a function of time, and hence an infinite dimensional object, representing the sensitivity of our objective function to the perturbations of the control. Okay, how can we compute it? Well, this can be done in the following way. So first of all, we'll need to recall a result from basic functional analysis, which is known as the Riesz theorem. Which says the following thing. So I'll adapt the statement of this theorem to the notation I've been using. So if J prime for some fixed f, okay, is a bounded linear functional on some space X, on Hilbert space X, then the action of this the action of this bounded linear function on some element phi prime can always be represented using the inner product of that argument phi prime on that Hilbert space X. This is a very useful result in this context, which provides the mathematical foundation of this type of computational approaches. It offers the possibility of a very elegant and computationally very efficient method to compute the cost-functional gradient, which otherwise would be a big hassle. Okay? So what does this mean practically? If this guy is a bounded linear functional with respect to the second argument, which of course requires a separate proof, but such proofs are available for many systems of interest to us here, then this theorem tells us that the action of this functional on some element phi prime can always be represented as an inner product on the Hilbert space X, where in our case X is L2, where one argument of the inner product is our element phi prime, and the other element is the so-called Riesz representer, which in our case is simply the gradient. Okay? So what can we do with this? Well, I guess what we should do first is we should go ahead and compute the Gateau differential of this cost functional. Okay? We try to use this theorem, and to do so, the first step is to compute the Gateau differential of our cost functional, which we can do right away. And what we obtain is this. Gateau differential of J of phi. So, well, I can compute it explicitly. So J prime at phi in the direction of phi prime is given by this, by the Gateau differential of this guy. So we have to apply this formula with the limit, okay? And then what we get is this. We have an integral from 0 to pi, or to t, I'm sorry. Here we have w of t minus partial u phi partial x at 0 times partial u prime partial x at 0 dt. We have one new object in this expression which we have not seen before, namely u prime. What is u prime? U prime is the solution of the linearized governing equation, of this governing equation, linearized around our phi. Okay, this is linearization of the system around the point where we compute the Gateau differential. Okay, how do we compute the equation governing phi prime? Well, we simply substitute phi plus epsilon phi prime for phi, and then just collect leading order terms in epsilon. So when we do this, the governing equation for phi for u prime will have the following form. So the equation itself doesn't really change. The Dirichlet boundary conditions become homogeneous at the left boundary. However, at the right boundary, we'll have the control perturbation entering as the boundary condition. And that's actually very important and very useful. And the initial condition is becoming homogeneous as well. Okay, so this is what we call the perturbation or linearized system. Now, okay, so, well, here is our Gateau differential. And the question is, can we already use it to apply Riesz theorem? Okay, so let's revisit the Riesz formula. What is so special about the Riesz formula? Well, what is special about this formula is that the argument of the cost functional of the Gateau derivative must enter as a factor. Does phi prime enter as a factor here? Well, not really, because what we have is u prime here, okay, and phi prime shows up as a boundary condition. It's hidden as a boundary condition for this in the system governing u prime. Okay, so the bottom line is that this form of the Gateau differential is not yet consistent with Riesz representation, and we have to do something to transform it to a form where we could apply Riesz theorem. And here is how we can do this. So the key enabler, key device that will make it possible is the so-called adjoint calculus. Okay. So we'll have to cleverly use adjoint variables and correspondingly define adjoint system to re-express the Gateau differential, which is given here, in a form that will be consistent with the Riesz formula. Okay. So what I would like to do now is just show you how it works. Okay. And I guess just to make a short digression, this heat equation model is actually quite useful because it is simple enough so that we can do these calculations in 3, maybe 5 minutes, and yet it captures the features of the problem shared by equations describing much more complicated and relevant situations. Okay. So how do we do this? Maybe I'll rewrite the Riesz formula here in this. Yes, a good point. Maybe I'll. Okay, so Riesz formula. J prime phi prime is equal to inner product of the gradient and phi prime in the space X, where X is the Hilbert space. All right. So how do we do this? Well, we have to introduce the adjoint variables. So my adjoint variable u star will be defined again on the Cartesian product of the time interval and our from 0 to 1 with values nar. And the calculation goes as follows. Let me start with this equation. I'm just going to rewrite this equation here, except that I'll put 0 on the left-hand side. So we can partial u prime partial d minus Laplacian u prime. Okay. Now what I'm going to do is I multiply my equation by the newly defined adjoint variable u star, and I'm going to integrate this over space from 0 to 1 and over time from 0 to capital T with respect to dx dt. Then what I'm going to do is integrate by parts. Now, all the calculations I'm presenting here are formal. Okay, so in principle, for problems where there are doubts regarding whether or not the different transformations make sense from the analysis point of view, separate proofs would be required. But that's not the goal of my presentation. Okay, so what we are going to do is to use integration by parts with respect to space variables twice, and once with respect to the time variable. Okay, so when I do this, I obtain the following set of expressions. We have integral from 0 to t, integral from 1 to n, u prime minus partial ut star partial t minus Laplacian u star dx dt. These are the terms defined on the interior of the time-space domain. In addition to this, we have a bunch of boundary terms resulting from integration by parts. So we have terms defined at the initial and the terminal time, which will have the form of integral from 0 to 1, u prime u star at terminal time, u prime u star at initial time dx. And in addition, we have a whole bunch of boundary terms. Now, since we are in a one-dimensional case, there won't be any line integral. There will be just time integral. So here we have u prime at 0, u partial u star partial x at 0 minus u star at 1. Sorry. Okay, u star at 0, u prime at 0 minus u prime at 1 partial u star 1 plus u star at 1 partial u prime. Okay, I think it's all we need. Okay? And now what we have to do is, well, look carefully at those different terms and see which of them will go to 0. Okay? So know that at this point, I haven't said anything at all about what sort of equation my adjoint variable is going to satisfy. But I'm going to do this now. So I postulate, somewhat arbitrarily for the moment, but you will see a justification for this in a second, that the adjoint system will satisfy the following, the adjoint variable will satisfy the following equation. Once I have said that, we immediately observe that this term goes to 0. Okay? Now, we also know that u prime at 0 is equal to 0, which means that this term goes away. Okay? Now, I do have some freedom in defining the adjoint system. In particular, I can choose what sort of initial and boundary conditions the adjoint variable should satisfy. And I'm now going to put this freedom to good use. So I'm going to postulate that u hat at t will be equal to 0. Which proves that term. Okay? What else can we say? Well, we can say that we see that u prime at 0 is equal to 0, which takes out this term. And then we also observe that u prime at 1 is phi prime. U prime at 1 is phi prime. So this thing is actually phi prime. Now, I guess we are starting to see wrist structure slowly emerging from this calculation. Okay? Because now we see the control variable, the perturbation of the control variable phi prime appearing as the factor. Okay. What else do we need to do? Well, let's say that well, we cannot say anything about partial u partial x, partial u prime partial x, but we can postulate that the adjoint variable u star at 1 will be equal to 0, which takes out this term. So all that is left are just two terms. One has already a more or less fixed structure. There is one more that remains. And this is a key step. So let's take a look at this term and compare it to the Gato differential. Okay? What do we see? Well, they share the same factor, here and here. And we also observe, if I impose the following Dirichlet boundary condition for the adjoint variable at the left endpoint, namely, I'll say that u star at 0 is equal to w of t minus partial u phi partial x at 0. Okay. If I impose this boundary condition on the adjoint variable, this will be exactly my Gato differential. Okay? So by making a clever choice in the boundary conditions defining the adjoint system, we've been able to somehow re-express the Gato derivative. So what's the final outcome? Well, please note that all that has remained from this calculation are just two terms. And since we started with 0, they have to be equal to each other. Okay? So from this we obtain that j prime at phi in the direction phi prime, which is this expression, is simply given by what? Is given by this expression, which is an integral over time of partial u star partial x at the point 1 times phi prime dt. So lo and behold, after this transformation, we obtain an expression which is precisely in the Riesz form. Okay? In the sense that the control perturbation appears as a factor in this expression. Okay? So what's the conclusion from this? Well, the conclusion from this is that since this expression is now in the Riesz form, we can immediately identify the cost functional gradient. Well, the cost functional gradient computed at phi is simply partial u star partial x at 1. Okay? So all we need to do in order to evaluate the gradient is solve the adjoint system. Okay? And then evaluate the solution of the adjoint system, actually the derivative of the solution of the adjoint system at the right boundary. Okay? There is a couple of remarks in place. So for evolutionary PDEs, the adjoint system tends to be a sort of curious animal. Why? Note that this is actually no longer an initial value problem, but a terminal value problem. Okay? Because this condition is imposed at the final time. Okay? So for evolutionary PDEs, the adjoint system has to be actually integrated backwards in time. Okay? Now we have a heat equation, so you may be worried about having to solve backwards heat equation, but that's actually not the case because there's a minus sign in front of the time derivative term. Okay? So when integrated backwards in time, this system is actually well posed. Okay? So okay, so that's all we basically need to to be able to evaluate the gradient for our problem. So what information is required to get this gradient? Well, at any given iteration, okay, we have to solve the governing system forward in time. And then using this solution, we have to solve the problem backwards in time. Solve the system backwards in time. And these two solves actually provide enough information to evaluate the gradient. Okay? And that's how those problems are solved. Okay, so maybe that will be enough in terms of this development. And I guess at this point, unless there are some questions, if this is not the case, then I'll probably go back to my presentation and show how this methodology can be applied to solve well, real-life problems like the control of the cylinder wake. Sorry? That's right? Yes? Well, that's what I said earlier. So I'm just interested in, at this stage, I'm interested in the structure of the expressions that can be used in the computations. Questions related to regularity, well, deserve separate study, and this is the area of research of analysts. I'm mostly interested in. So for this particular problem, where we are just dealing with heat equations, so it's not a big deal. Those issues, namely the questions concerning the regularity of the agent problem, are very relevant for systems with more complicated. And that's an area of well, intense study. Okay? Yes. Yes. Yes, that's a good point. So what is tau? So this expression nabla j is the gradient. Okay, it points the if you are in the infinite dimension, if you put yourself in the infinite dimensional space of control, nabla tau, nabla j represents the direction of the steepest descent. Now tau represents how far along the this direction we want to go. How can we find this? Well, let me just do a brief digression to address this issue. Maybe I'll use the whiteboard. Okay. So how to determine tau? Well, this problem in numerical optimization is referred to as line minimization. Okay? So how do we do this? Well, let me define a new function, f of tau, which is defined as follows. So j evaluated at phi n minus tau nabla j at tau n. Okay? So it's I have defined a new function, f of tau, which describes how my cost functional depends on the length of the step size. So in other words, I'm looking at the cost functional, but only along the direction of the steepest descent. Okay? So typically, when you plot this function, this is f of tau, typically something like this. If the problem is has the right structure, typically see this, okay? And how do we find tau n? Tau n is found by the solution of the following problem. We are just looking for the minimum of this function with respect to tau. And there is this is a very well-developed area of numerical optimization, which provides a number of different algorithms that can solve this problem. So basically, they all rely on one idea, namely they sample the function for different values of tau and then interpolate the results with various accuracy, and in doing so just sort of bracket the minimum. Okay? There is an almost infinite number of versions of those algorithms, but they are all variations of this one idea. Okay? One algorithm, if you ever wanted to solve this problem in practice, one algorithm that is particularly well tested is called Brent's. Okay? And this is a simple yet rather tedious step, because anytime we evaluate f, we actually have to evaluate the cost functional, which means in turn that we have to evaluate the governing equation. Okay? So it's quite costly, although conceptual is very very straightforward. Okay, so there are a variety of ways in which this can be solved with more or less accuracy. Okay, so at this point, unless again there are some questions, I'll move back to the presentation to show you how this methodology can be applied to solve real problems. Okay, so I guess what I need to do is lower the screen. And ask someone to turn the projector back for me. Yes? Okay, in the middle, like here? Yeah. All right. Okay. Okay, so okay, here it is. Okay, so here is again our cost functional, the one that we introduced at the beginning of the lecture. Now, if we compute the Gateau differential, here is the expression that we obtain, and we see that it depends on p prime and v prime as the perturbation variables, and the perturbation of the control, which I denote h, is not present here explicitly. So what we need to do is introduce the adjoint system that will actually allow us to re-express the const functional in a convenient form. So v prime and p prime solve the perturbation equation, which is given here. So when we go through this calculation, which is again technically slightly more complicated than for the heat equation, but the main principles apply. One has to integrate by parts and then match the terms. Then we obtain the adjoint system, which, as before, is a terminal value problem, which means that it has to be integrated backwards in time. There is one more sort of important difference with respect to the heat equation example, namely for the heat equation, the adjoint system, which I guess we can still see here, is essentially the same as the governing equation, except for the sign of the time derivative term, which is different. Okay, the Laplacian term, because it's self-adjoint, is of course the same. Now, this is no longer the case for the Navier-Stokes system. The reason being the presence of nonlinearities. Okay, when we compute the perturbation equation, we obtain these two terms, and then they are, of course, not self-adjoint. That's why the corresponding terms in the adjoint system are rather different. Okay? So the bottom line is that if you have a problem that has non-constant coefficients or is nonlinear, then the adjoint system will be different than just the linearized equation. Okay, although not that different. What does it mean practically? Well, practically, it's important because to be able to solve this problem, one has to develop the code for the solution of the adjoint system. Okay, and the more differences there are between the direct and adjoint system, the more extra work will need to be invested in order to implement the adjoint system. Okay. So again, we take advantage of the freedom that we have in defining the adjoint system, in particular picking the right initial and boundary conditions. And when we make the right choices, here is the expression that we obtain for the Gatot differential, now given in terms of the adjoint variables, in which the control perturbation H enters explicitly. So this is in the RIS form, and from this we can directly extract the expression for the cost functional gradient, which we can in turn use in our optimization algorithm. Okay, so this is the expression for the cost functional gradient that can be used, and it's actually readily computable. Once we have solved the adjoint system, it can be evaluated quite easily. There's one more aspect, sort of technical, that comes up in a number of applications. So for simplicity here, I assume that the control I seek was an L2 function of time. How about if I require more regularity of the control? In particular, if I require that my function phi be actually an H1 function of time. Okay. So what would happen in that case? Maybe I'll do it in order not to have to turn off the screen. I'll do a quick calculation on the on this blackboard here. So what I would like to show in this calculation is that this framework relying on the RIS theorem admits a very straightforward generalization to finding solution living in other Hilbert spaces other than L2. So now we are looking for the control H, which lives in H1 of 0t. What do we do? Well, so we have our Gatot differential, okay, and after applying the adjoint machinery, this is the expression that we obtain. Okay, so we have partial u star partial x at 1 phi prime dt, and now I'm going to say that this is equal to an inner product, but in the space H1. Okay, now it's going to be equal to the inner product in the space H1. So let me write out explicitly the expression for this inner product. So this will be an integral from 0 to t. And here we have my gradient in H1 phi prime plus some characteristic time scale, let's call it L squared, partial JH1 partial t, partial phi prime, partial t dt. Okay? So by identifying the Gatot differential with an H1 inner product, I'm equating this with this. And what I have to do now is integrate by parts and impose some boundary conditions. And if I do this, I obtain the following problem. So identity minus the parameter L squared second derivative with respect to time, my H1 gradient is equal to the minus L2 gradient. And the boundary conditions are the H1 gradient is equal to 0 at initial and terminal time. So what's the bottom line? Well, if we do require more regularity, then the corresponding gradient in the Sobolev space H1, or whatever Sobolev space we choose, provided this is still a Hilbert space, is obtained by a solution of this elliptic boundary value problem, this two-point elliptic boundary value problem in time, where the right-hand side source term is actually the L2 gradient. Okay? So the L2 sensitivity on the right-hand side gives us, via the solution of this two-point boundary value problem, a gradient which is defined in the space H1. If we are looking for a gradient in H2, it would look similar, except that we would have a fourth-order differential operator here. Okay, so this is a very simple device to impose more regularity on the gradient. Why is it important? Well, if we want to construct a solution that has, if we want to construct control that has some degree of smoothness, this is a device that makes it possible to enforce this regularity in a straightforward manner. What I would like to emphasize is that computing this gradient, well, one has to invert this elliptic operator, which actually has the structure of the low-pass filter. Okay? So this is actually a smoothing operation, okay? Where this parameter actually serves as a sort of cutoff frequency. So this was just a digression. Okay, so back to our Navier-Stokes problem. When we put all different pieces together, we obtain the complete optimality system, characterizing the optimal control, the corresponding optimal solutions, and the associated adjoint variables. So there is clearly a very close connection between adjoint variables and Lagrange multipliers. There are also differences, though. While Lagrange multipliers are typically defined at the optimum only, adjoint variables make sense away from the optimum, in which case they, however, admit the interpretation of sensitivities of the state variables with respect to various perturbations. Okay? So one can think about this equation as the counterpart of the Euler-Lagrange equation. Okay, so what does the actual computational algorithm looks like? Well, it's an iteration that basically implements this formula in the following steps. So we start with some initial guess for the control, for instance, 0 or whatever educated guess one can come up with. Then one solves the governing system corresponding to this particular control, and then one solves the adjoint system backwards in time. Okay? So one needs a forward sweep for the governing equation and a backward sweep for the adjoint equation. Now, with these two solves, one can evaluate the cost functional gradient, which in our case is a function of time, and then use this gradient to actually update the our approximation of the control. And one iterates this until convergence, which may be characterized, for example, by the vanishing of the gradient in some suitable sense. Now, one more remark. So here, and here, we are actually using the steepest descent algorithm. However, in practice, one uses more advanced descent algorithms, such as, for instance, conjugate gradients, at the cost of a very minuscule modification of the computations. One obtains a much more robust and rapid convergence. So some results. So what I would like to show you now is the solution of the direct and adjoint system for this problem, which looks sort of curious, I have to admit. Let's see. So this guy is still running. Okay. So there are two frames. Okay, there are two animations. The top animation represents the solution of the governing equation, which is basically a magnification of the solution I showed you at the beginning of the lecture. Okay, whereas the bottom frame represents the solution of the corresponding adjoint system at the same instances of time. Now, since this is a terminal value problem, we see that the solution vanishes at the end of the time window. Okay, so we go through the time window. This is the end of the time window right now, and we see the solution vanishes because this is a terminal value problem with homogeneous terminal data. Okay, so this solution would actually, the adjoint solution, would actually look more natural if it were run in the adjoint time, running backwards, because then it would actually grow upstream. And let me reiterate that the meaning of this adjoint field is that it conveys information about the sensitivity of the governing field to our control. Okay? So these results that I have just shown you is actually an animated GIF file, which is a technology one used to produce animations 15 years ago. Because this is basically the time when I was working on this problem. I guess at that time it was an open problem. Now people have been applying this methodology to solve a very broad range of complicated problems. And those methods have become some sort of industry standard for solving PDE constraint optimization problems for complicated PDEs. Okay, let me show you some quantitative results to demonstrate that it actually produces something useful other than just colorful pictures. So let me remind you that the goal was to get rid of the vortex shedding, or at least partially mitigate the detrimental effects that vortex shedding generates. So that's the flow that you get without any control. And now this is what happens when you switch the control. And you see that as compared to the original flow, while we don't really manage to get rid of the vortex shedding, the flow does indeed become more symmetric. Okay, and this is, for example, what happens with the drag force. So we obtain that we see that we obtain almost 20% sustained drag reduction versus the case without the control. So well, that's measurable. When you try to translate this into questions arising in say aerospace engineering, when they build aircraft and think of the savings that 20% drag reduction would give you. And by the way, that's the history of the control, which means that it's actually quite jagged. Why? Well, we solved the problem in L2. So, well, we got what we asked for. We just got an L2 function, which doesn't seem to have any smoothness. This study was carried out a long time ago, and since the time we learned how to compute solutions with much more smoothness, namely using this methodology. Okay, so unless there are some questions, I'll use the remaining 10 minutes or so, at least to get started with the second problem concerning feedback control. Yes, madam.
How did you calculate the adjoint?
Oh, you mean the numerical method? Oh, that's a good question. So in this study, okay, so the entire formulation was based on the continuous adjoint. which means that the adjoint equations were derived at the continuous PDE setting and only then discretized. As you mentioned, there are actually two possibilities of setting up the problem. Since ultimately we do have to discretize the problem for the purpose of the numerical solution, this can be done either at the beginning or at the end. So what I described earlier is the so-called optimize then discretize approach, where the optimality conditions and the entire optimization formulations is developed at the continuous PD setting and discretized at the very end. But there's a different approach, as you suggested. Namely, one could start first off just by discretizing the problem, okay? And then one obtains essentially a finite dimensional problem, which doesn't have any infinite dimensional structure. And then one optimizes this problem. While the second formulation with discrete adjoints certainly has merits, especially for large problems, I think there the entire in continuous structure is lost, and all the subtlety of infinite dimensional problems is lost. Okay? So this was done using the continuous adjoint. And I guess what was original about this work was that the adjoint system was solved using the vorticity formulation. So we had an adjoint vorticity equation which was solved using adjoint vortex method. There's a class of numerical methods for solution of PDEs which basically track particles carrying vorticity. And this is the kind of method that we use here. So, I wouldn't like this to be the main topic of my lecture, but I will certainly be delighted to talk to you, to anybody interested about more details. Okay, so the first part concerned the use of PD constrained optimization techniques to solve, to determine open loop controls. So what we found here were open loop controls like this. Now, what I would like to do is switch gears a little bit and consider feedback stabilization problem. And as motivation, I would like us to consider these two snapshots of vorticity. So these two fields represent two solutions of the Navier-Stokes system corresponding to exactly the same boundary conditions, exactly the same domain, and exactly the same equations, of course. This is the unstable fixed point. Okay, this is a solution that we typically observe at small Reynolds numbers. However, as the Reynolds number increases, what happens is that vortex shedding develops, and this solution, while it still exists, is no longer observed because it's unstable. Okay, so when the Reynolds number is supercritical, this is the unstable fixed point, and this is the actually observed limit cycle. As I already said earlier, this solution has a number of very bad properties. It has large drag. It suffers from limitations. Yes.
Limitations from you have different really equations because you have different Reynolds numbers.
No, it is the same Reynolds number.
You said you change the Reynolds number and the same solution becomes unstable.
Oh, so what happens is if we just have one equation, okay, and for a fixed Reynolds number, which is small, and then we increase the Reynolds number, okay. So when the Reynolds number is small, subcritical, that's what we observe, and then we hit the Hopf bifurcation, and what we see in reality, I mean, in a real physical world, is this solution. This, however, still continues to exist, but we don't see it because it's unstable.
What you say is that the solution of the Navier-Stokes equation with small Reynolds number is also a solution to Navier-Stokes with large Reynolds number.
Oh no, that's not the same solution. Because
you said this solution still.
Okay. When I say this solution, I mean solution with this structure, with this qualitative structure. Yeah. Okay. So So yes. No, you're right. I was a little bit imprecise. when I said that this solution. By this solution, I meant solution with this structure, which actually changes from one Reynolds number to another. Okay, so I guess to understand this, one can draw a very simple bifurcation diagram.
Now it's fair.
Yeah, it's clear. Okay, but maybe just since this question did arise, so that's the Reynolds number, and this is some order parameter. For instance, the amplitude of the transverse velocity. When the Reynolds number is small, we observe this solution with zero transverse velocity, and then at the critical value, okay, we have vortex shedding. However, this solution still exists. It's a solution of the Navier-Stokes system, which is just unstable. Okay. So from the practical point of view, it is much more desirable because it has lower drag and doesn't have oscillations. Okay, so it's the goal. A lot of applied research in fluid mechanics is to devise control methodologies that would actually manage to stabilize flows with spontaneous vortex shedding and retain structure like this flow here. Okay. So this is from the control point of view, this is a stabilization problem, and what I would like to present here is an approach leveraging tools of linear control theory and applied to a very, very simple model of the problem. Okay, so in the remaining 5 minutes or so, I'll try to at least sketch some elements of that model. So how do we set up the problem? Well, as before, the rotation of the obstacle encoded by the boundary conditions in the Navier-Stokes system will serve as the control variable. Okay. Now we'll be talking about the feedback control, so we need some system output. We are not interested here in state feedback. We'll be interested in something more realistic, namely output feedback. And as the system output, we are going to use velocity recorded at some point in the domain. Why? Well, that's what experimentalists would typically do. They stick a probe into the flow and measure velocity. That's why this model was actually devised to sort of mimic what happens in the actual experiment. And the goal is to determine an optimal stabilizing feedback control law for this system. So this is, by the way, the target flow, which is the unstable fixed point for the Navier-Stokes system, and that's what we would like to stabilize. So at this point, I would like to simplify the problem a little bit and consider the other equation. In particular, I am going to consider some very special class of solutions of the other equations, which are known as the Prandtl-Batchelor flows and related flow vortices. Okay, so the steady-state Euler equation is written here. When we convert to the vorticity formulation, it can be written like this. So basically, what it says is that the time derivative of vorticity is equal to 0. And it's a well-known fact in fluid mechanics that steady-state Euler equations can be found as solutions of this nonlinear elliptic boundary value problem, where the function f on the right-hand side is actually a priori undefined. So this is actually it reflects the non-uniqueness of the solutions of Euler equations, because the function f can be found essentially arbitrarily. I'll just do one more slide, and I guess this will probably be a good point to stop for today. So one possible choice for the function f in this Euler equation here, where is it? It's right here, is which is motivated by the so-called Prandtl-Batchelor hypothesis, is to use f, which is a Heaviside function, which is either 0 or a constant. What does it correspond to? Well, it corresponds to a compact region with finite area, with constant vorticity, which is embedded in otherwise potential flow. Okay, and those flows are known as Prandtl-Bachelor flows. Okay, so we have a vortex patch with constant vorticity and potential flow outside. Needless to say, the boundary separating the vertical region from the potential region is a priori unknown and must be found as a part of the solution of the problem, which means that this is effectively a free boundary problem. Okay. Well, solutions of this type have been computed for a variety of configurations, and they exhibit a number of interesting features. They, in fact, in this setting, they represent a two-parameter family, and can be parameterized, for instance, by the circulation, which is just the integral of the vorticity over the patch, and, for example, the area. And here we have the Prandtl-Bachelor flows corresponding to a flow past an obstacle computed by my colleague Alan Elkrat. And the intriguing feature of this problem is that if you fix the circulation and you shrink the area to 0, then in the limit we obtain a solution with a Dirac delta, which corresponds to a point vortex, which actually admits a closed form representation, which was actually discovered by Feppel in 1913, and which consists of 2-point vortices and 2 images inside the obstacle, all in equilibrium. Okay, and the positions and circulations of those vortices are described by those remarkably simple algebraic relations. Okay, so let me emphasize that those flows are the terminal members of this infinite family of solutions with the finite area vortex patch. So those flows are referred to as Feppel flows, and will be the basis of the control design that I'm going to describe, well, tomorrow morning. I guess I'll stop here. I wouldn't like to infringe on the time of the tea break, and we'll be very happy to take any questions. Thank you.